All right, so I'm going to talk a little bit about edge computing, and I want to start with a few things that I think are important. And the first one is that people want to make better and faster decisions. People also want to manage their operating costs. Transmission costs, of course, being part of that, but ingress costs, et cetera, are also part of their operating costs in any kind of production environment. People also are very sensitive to the personal and private information, and this is always, I think, for many of us been true, but it seems to be getting even more to the forefront, especially with some of the things that we've seen recently, and ransomware and other kinds of attacks like that, but mostly just people getting sensitive to the impact that has on their business as well as on their personal lives. And then finally, people are very concerned about how they maintain the continuity of their business in the presence of all this technology and the potential for fragility in that technology. And so for all those reasons, we think that edge computing is becoming increasingly important. But it's not just me. I think we'll see here in a few minutes, the analyst data about the marketplace really reaffirms that there is a strong movement to get workloads closer to where people do their work. That's where the data is being created. It's on the factory line. It's in the retail stores. It's out in the vehicles and the roadways that we travel. That's where we are as people. That's where the data that matters to us is being created, either by ourselves or by the environment in which we operate. That's where we make our decisions, and the lowering the latency with which we can make those decisions, lowering the latency of the data processing that allows us to make those decisions, the ability to reduce the number of times that we might be just transmitting sensitive information across the internet, the ability to continue to operate even if somebody happens to dig up the network cables in front of our building. Any of those kinds of things begin to matter, and edge computing goes a long way to helping that. Now, when we talk about edge computing, we like to talk about three very distinct tiers of edge computing. The first of these being the network edge, and Eric called out the multi-access edge computing. This, the MEC, as we like to call it, actually services it in a couple different ways. The first is within the network facilities themselves. So whether that's a central office or a regional data center or a hub location, we are certainly seeing examples and occasions where the telcos, the network operators, are creating compute capacity in the network facilities. And of course, that's not just about creating a new cloud experience. It's really about bringing those workloads closer physically to where businesses operate, and therefore reducing the latencies associated with that. But beyond that, there's also compute in those remote on-premise locations where people do their work as well. It is not unusual, or let me say it differently. It's very common to find compute capacity in a data room, or sometimes even directly on the factory floor. They may be industrial PCs, they may be half racks, they may be appliances, but there's a lot of compute capacity out there on the factory floor. Or in the retail store. If you ever go to your favorite grocery store and if you get a chance to go back to the manager's office, there's a good chance you're going to see 5 or 6 or 7 PCs sitting there on a desktop in the manager's office of your favorite grocery store. They're getting a little bit more organized sometimes, a little bit more structured. There might be a network room in the store that they put that stuff in a rack. But nonetheless, compute in the retail store is very common. As we get to intelligent and connected vehicles and the intelligent roadside, you're going to see compute actually in the roadside infrastructure itself. And so that's the second tier of compute. It's in the remote on-premise locations. And we call this out distinctly because typically what we find there is IT-like equipment, stuff that we would all recognize as a server in any other form. But the last one, which I think is really interesting, are the edge devices. And Eric kind of alluded to this a bit. Almost all equipment that we deal with, whether that's in our work or our home, there's a good chance that equipment now is being built with ARM or x86 chips, sometimes with small capacity, and some of that's because of if they're mobile devices and battery operated, we do have to be sensitive to the power consumption they have. But also in other cases, it's just cheaper and faster to build your device if you've got a general purpose computer in there, and you can run Linux and perhaps a Docker runtime in the device itself. And what I'm talking about here are things like intelligent cameras, right? There's a good chance that the cameras that we have here in the room have a computer in it. The industrial robots that you see, and you'll see some examples of this later on when we talk about Spot. These are things that have computers in them. The stuff that we don't even think of necessarily as being a computer, certainly we wouldn't think of it as IT equipment. We might think of it as OT equipment. There's a good chance that it has compute in it. And when we think about the capacity that each of those represent and the location that each of those have relative to where the data is that we're generating, where the work is that we're performing, and the data that we generate, each of those have a potential role. And we can now start thinking about how to get some normalization across that. As I said, a lot of the equipment that have computers built into them, what we call edge devices, are already running Linux. They may be running Docker. The edge servers that we talk about, or the dedicated Macs, the 5G private Macs that we see out there in the roam and on-premises locations, are probably running some form of Kubernetes. Certainly, the facilities that we see, the compute that we see within the network facilities, are all running Kubernetes, generally speaking. And so what becomes interesting here is the idea that cloud-native development practices can be applied for creating workloads that will run on any of these tiers, including the cloud, of course, right? And when I say cloud here, I mean, of course, public and private data center clouds, whatever the form is. But cloud-native development practices seem to be taking hold as the dominant form of creating application workloads. And when you have that kind of consistency across all those tiers, it really opens up to the idea of multi-tier distributed computing applications, which of course is not a new idea, but it's an idea that's coming back because of this normalization that we're seeing across all these different tiers, and the ability to take the same development practices that you would apply to building applications in the cloud can now also be applied to all these other tiers as well. And that becomes really important when we think about AIs here, and you'll see that surface more in a minute. Just to make a point here, however, IoT is another term that you'll hear very commonly when we talk about edge computing. A lot of people sort of think of edge computing as being born out of the IT era. And in some sense, it is. Obviously, what we're talking about here are devices that can be connected and for which we can use internet protocols to access and communicate with. But there's an evolution. Whereas in the past, IoT devices were typically, built with ASICs. They were relatively dumb or fixed function. They had sensors, and you would use them to kind of connect and collect sensor data off of those IoT devices that you might then transmit back to the cloud. Today, with the introduction of edge computing, we can begin to process that sensor data more locally, if not on the sensor itself. As I said, some of that's now turning into what we call edge devices, merely by virtue of the fact that we have added a general purpose compute capacity in there and have the flexibility of deploying other workloads. We can now consider those traditional IoT devices edge devices, but even when they continue to be sort of, if you will, dumb sensor data devices, we can still connect those to localized edge devices or edge servers, et cetera. As I said, the growth of edge computing is just phenomenal, and this is some Gartner data that was published in a couple of different papers. But if we presume last year 10% of compute was done at the edge, 90% is being done in cloud or IT data centers. As we move into next year, we expect that to be closer to about 50%, and this is not far off from what we're actually exhibiting in the field today. Already a tremendous amount of the data that you create in these locations, whether it's on the factory or the retail or otherwise, is being actually processed locally in those locations. As we move into 2025, we think that as much as 75% of all enterprise data that is created in these locations will be processed there. And that's not to suggest that cloud computing goes away. If anything, cloud computing continues to grow, and its growth is accelerated by the growth of edge computing. This is a phenomenon that we experienced back in the days of client server, and again in the era of SOA and web applications. These kinds of technologies tend to drive a lot more transactional demand to the back end, so we should expect to see that here as well. The difference being, of course, that when we're doing that more efficiently. What we're using the cloud for is something that's more specific to the value that cloud processing brings to us. But again, the point being that we've had this point of normalization, and we examine the utility that each of these different tiers bring to the table, we can now begin to think about the trade-offs between cost and performance. We can think about where is the right place to put our workloads based on the utility that workload has and the dependency that workload has on things like latency. The further you get close to where the data is being created and where the decisions are being made, the lower the latency you can create by doing your compute there. It's a pretty obvious example, but that's a premise that we can exploit across every tier. And now we can right-size the placement of workloads, knowing that these are not necessarily architectural assumptions that we have to bake into the solutions that we produce. We can, in fact, today decide to put workloads in the cloud that tomorrow we can change our mind and move that workload closer either into the network or an edge server or perhaps even onto the edge device itself. Or conversely, we may over-optimize and realize, and by placing workloads really on the device and then later realize that we have either competing demands for that limited resource or the cost of running it there is too high for the value that we're getting from it, and so then we can begin to migrate workloads back from the far edge back into more near edge locations. And so for the first time, I think, in the history of our information systems industry, we've truly had the ability to make cost-benefit trade-offs over the placement of workloads and be able to make that flexible over time. So this is a key thing for us to be considering. And if you're wondering what I mean when I talk about edge computing devices, I've just given you a very small sample of the huge array of edge computing capabilities that are out there on the market already today. And you'll see here sort of this wide range of things that are general purpose compute and highly specialized compute. In this case, HP retail systems. These Eurotech bolt gates are designed specifically for industrial environments. Of course, you can see things like industrial robots and intelligent power controllers. So a wide range of the kinds of things that have compute in it today. All of these things run Linux. All of them have either Docker or the Kubernetes runtime, Kubernetes platforms running in them today. And again, I want to emphasize this is just a very small sampling. Where are we seeing the application of edge computing is most often is around things like process optimization, situational awareness, which might be for worker safety or things like that. Human-machine collaboration is becoming a very important thing, and in fact, I'll talk a little bit more about this later on when we talk about cobots. Of course, lots and lots of AI. The most commonly referred to workloads that we hear today in the edge computing space tend to be some sort of AI-based workload, whether that's visual recognition, Eric talked a little bit about that, whether that's acoustic recognition, whether it's just stream data analysis. AI of various sorts are the kinds of things that we typically find out there, and primarily because these things tend to be very data intensive. And the cost of transmitting that data is not only high in terms of operating cost, but also you lose the benefit of latency when you have to move all that data back up to the cloud, process it there, and then eventually turn it back around. If you have to suffer 100, 400, 500 milliseconds of latency, that may be fine for human interactions, but when it comes to machine and in industrial processes, and you're doing, if you've got manufacturing processes that are putting out 100 widgets a minute, a half-second latency to make the decision whether to reject a quality problem is way too long, right? You need to make these decisions much faster than that. We're seeing this being applied primarily in industrial and manufacturing scenarios. Secondly, in infrastructure, and when I say infrastructure here, I mean roadsides, buildings, maintenance kinds of problems. Retail is a really hot area right now. You see a lot of interest in the retail industry, especially as a result of COVID, and I'll talk a little about that in a minute here too, to automate and reduce the amount of touch, if you will, in the retail settings. If you were a retailer, you certainly had to figure out how to get, buy online, pick up at the store processes in place. So a lot of retail, of course, the Amazon Go concept is taking hold in the retail industry. Everybody wants to kind of move towards a more intelligent store, automated checkout kinds of scenarios in the retail space, and of course services. Data is an ongoing, I mean, we've been talking about in the AI world, the growth of data for a long time here. Well, this is very real and it's very expensive. People can't keep up with the rate at which new data is being generated, and they can't process it. They simply don't have the capacity and the wherewithal to process it. When you bring tons and tons of data back into your data center, into your cloud, it's great that you have this huge data lake, but what are you going to do with it? And figuring out how to build the analytics for that is always a difficult task, especially given the specialties that we need around data scientists to be able to do that with. The more that we can fragment the data and deal with it in flight, the more that we can filter it, that we can reduce it and get it down to the most essential and relevant data for us with any of our operations. The earlier that we can do that in the process, the better. And so that's another reason why edge computing is becoming really important. I've talked a little bit about the growth. Just to put this in numbers, 21.5 billion devices will be connected to the internet by 2025. 21.5 billion. Think about in the world of mobile computing, right? Today we have something like 3.25 billion mobile devices in the marketplace today. This is a multiplier number of devices that will be connected. And again, these are not just dumb IoT devices. These are pieces of equipment that have chips in them that you can compute on. The reason why SoftBank paid what they did for ARM and why later NVIDIA has been so attracted to the idea of purchasing ARM is because of the growth of the number of chips that are going to be consumed in these kinds of devices over time. There are a lot of changes that are occurring, especially in the workforce and around processes, both in industrial but also in retail. And I hinted at this before, largely due to the impact that COVID-19 is having on the way that we do business. If you're a retailer, as I said before, you need to reduce your touch footprint with your clients. The retailers that were able to stay in business during the sort of the economic crisis the pandemic introduced were the ones that gravitated towards digitalization. That introduced buy online and pick up at the store, pick up at the curb. If you go to your favorite restaurant, whether it's here in the city or anywhere else, chances are you're going to be exposed to a QR code to get your menu. And of course, that's just step one towards a more automated ordering system. Sooner or later, we may not even have servers in some of the best restaurants because everything will be digitalized, even in the restaurant. If you're in the store trying to track spillage, spoilage, loss prevention, any of those kinds of situations are requiring a more digital presence, digital footprint in the store. Pharmacies, if you're a CVS or a Walgreens and you've got pharmaceuticals in a refrigerator and somebody actually leaves that refrigerator door open and the temperature inside the refrigerator rises overnight, you could easily lose $10,000, $50,000 of pharmaceuticals just in that one incident. So the cost of outage is the cost of these issues is really high. If you lose connectivity to your store, some retailers will tell you it may cost them between $50,000 and $100,000 an hour while they are offline in that store. Obviously, not the ability. If you lose the ability to check people out, you're losing revenue. If you lose the ability to serve your clientele, you could be impacting experiences, creating issues for you for trying to get those consumers back. If you are a grocery store and you support, and I forget what the acronym is for it, but basically food stamps or food vouchers, the law says that if you cannot check a person out and they're trying to pay with food vouchers, the food is free. Right? So an outage is very expensive for retailers, and trying to maintain their productivity during that time is really key. One example of the use cases that we see today is the application of visual inspection and visual recognition for quality inspection. This particular case, we're using infrared. This is at a manufacturer that does welding. If you're familiar with the welding processes, one of the things that has always stymied the industry is how do you ensure the quality of your weld activities? Typically, in order to tell whether a weld was done well or not, whether you have a quality problem or not, you have to take whatever it is that you just welded and take it off the line, cut it open and look inside, or you might be able to do x-rays, but even that requires taking the product offline to go do that. Very expensive process. It's destructive. Obviously, if you run into a problem, because you're not going to sample every single car that you weld or every weld that you perform, you're going to take samples, which means that if you had a quality problem that occurred earlier in your cycle before you caught it, now you got to go remediate over all the different pieces of product that you had welded previously. So in this case, what we've done is we've taken an infrared camera, we've trained it using machine learning to recognize at the moment that it's being welded whether it's a good weld or not weld by virtue of the heat signature on that weld as it's being performed. Now, these are capturing full resolution video to be able to do that. In a typical manufacturing spot, you may have 100, 200, 400 robots, each doing welding activities. And if you have a camera associated with each one of those, and you think about the amount of video data that generates, you could easily overwhelm your networks trying to get all that data back up to the cloud. On the other hand, the amount of time that you're actually examining for quality is only a subset of the total time that that video camera is on. So you want to be able to turn on or turn off the camera, or at the very least, you want to filter it, because the only thing you really care about is that one frame that indicated a failure, a quality problem. All the rest is interesting, but somewhat superfluous. And if you do all that processing locally, not only can you reduce the amount of data that you have to transmit back to the cloud, you're still going to transmit the outcomes of that evaluation, the inference results back up to the cloud, but that's a much smaller quantity of data than the actual raw video stream itself. So we do that processing online there in the factory. We may actually activate into the OT system, reject processing and remediation if we do find a quality problem, and then we report any kind of inferences that we got out of that process back up to the cloud. The other thing to be thinking about here is the data, even AIs, that we might consider here, whether that's for predictive maintenance, whether that's for asset management and monitoring, getting the data has always been a problem. Any of us who've been involved with machine learning know that getting the training data is always a hard task. It's probably the most significant issue that we have to deal with. If you're in a factory that's been around for the last 20, 30, 60, 100 years, you've got all kinds of equipment on that factory, which is not digital. It's hard to get the data off that equipment. You've got analog gauges, you've got physical control valves and other things like that you have to deal with. It's not digital. A very small percentage of the equipment on any given production environment is digitally enabled. And so the question is, how do you get data from a real world situation when everything is analog? So because of that, and because of the cost of upgrading everything to digital, we've been working with Boston Dynamics because it basically introduces a way of bringing data capture into the world in a very mobile and flexible way. We call it dynamic sensing. And essentially taking a Boston Dynamics spot robot. In fact, there's one out here. I saw one at the Deloitte booth. And putting sensors on it and then using it to navigate across the production environment is a great way of overcoming some of those deficiencies in a production environment where everything is analog. We call these cobots because they're collaborative. They typically work with humans, not in place of humans. There may be some replacement in the case where humans today are exposed to arduous situations. It may be a safety benefit to send a robot out onto certain production environments. Certainly there's a lot of heat, there's a lot of noise, there's a lot of other things that are unpleasant for humans to interact with. So there may be that, but in any case, these are typically working alongside humans, so we call them cobots. This is an example of where we applied it. Now, we actually took this video in the Boston Dynamics factory, but we're working with a number of customers in running the same use case in their environment as well. In this particular case, what we're doing is using Spot to go around and do fire extinguisher inspections, right? So we know where all the fire extinguishers are across the factory. This is a task that humans today have to perform generally on a monthly basis. They have to make sure that all the fire extinguishers are in place, that they are not obstructed, that they're properly pressurized, that the hoses and so forth are properly connected and so forth. So instead of a human doing this task, we can send Spot out. It will go to each location. Now, Boston Dynamics has done a phenomenal job giving Spot the ability to navigate and traverse in sort of unpredicted environments. If you think about the plant floor, you may know where you need to go, but getting there is going to be exposed to all kinds of things that you didn't anticipate, like equipment being moved in the way, or you probably saw earlier where Spot stepped over another Spot robot that was sitting down on the floor. Their ability to navigate around really tight areas is phenomenal. But what we've done here again is we've taken the camera on Spot, we've added visual recognition to identify in this case that the fire extinguisher is there, but it's obstructed. There's stuff in front of it. And what we do is we automatically issue a work order, in this case through Maximo, to get a work crew out there to fix that situation. So this is a task that Spot can do quite well. And other things that we use Spot for included, 2 minutes, oh wow, time's gone fast. Okay. Other things we use Spot for is to also look for, we actually read gauges. So it can walk up to an analog gauge and read it, and then basically transmit that digital information back to our work environment. Okay, since I'm down to only 2 minutes, let me hit a couple other points real fast. One is we did this work with Mayflower. Mayflower basically is a project to navigate from Plymouth, England to the United States in a ship that's fully autonomous. There is no human beings involved with this ship. There's no crew quarters. There's no space for anybody to be on board. It will navigate itself from one side of the ocean to the other. Again, to be able to do that, we had to have compute on board. It has to have the ability to recognize the obstacles it may encounter along the way, whether those are other ships or navigation things, whether it's shorelines and rocks and other things that you need to avoid. Sometimes there's debris in the water, containers that fell off another ship. It has to navigate around. And of course, there's all kinds of marine life out there that you have to navigate around as well. All of that has to happen on board. There's very few cell towers at sea, so our communication is typically through satellite and with very low latency, low bandwidth. And so we can't kind of do any of that kind of processing on site. And so I'm going to jump over that. By the way, one of the side effects of this is not just simply the technology of autonomous navigation, but all the marine science payloads that we can put on board. So if you think about the ship navigating the oceans for weeks or months at a time, collecting science data that can be then used for evaluating the health of our oceans, the impact of climate change, et cetera, that's an enormous benefit that we can get and cost reduction. If you want to learn more about the Mayflower project, you can go to maz400.com. I put a QR code there that you can capture that'll get you there too. All right, let me wrap up here real quickly with one last point. We talk about edge computing, but it's important to understand that while we are leveraging cloud native development practices, the edge is not the cloud. There's a fundamental difference between the cloud and the edge. The cloud typically is centered around a lot of homogeneous compute capacity. What we're looking for is lots and lots of services that all look the same so we can get elastic scalability over infinite resources, virtually infinite resources. The edge is very different. Eric already talked about this. Lots of diversity at the edge. A lot of dynamism at the edge. The stuff moves around, it gets repurposed, it gets reconfigured. A lot of security attack surfaces at the edge because we've got people walking around this stuff. It's not locked up in a room with 4 walls and armed guards and so forth. And for that reason, managing getting the right software to the right place at the right time, getting the right AI out there and keeping up to date, keeping the models up to date is a task that we've taken on. So my one plug here is for a product that we built in IBM called IBM Edge Application Manager. Its purpose is to get the right software to the right place at the right time. That's what we do. We do it at scale. We can support up to 40,000 edge nodes. It is based on open source. We derive this from an open source project that we contribute to. There's a vibrant community around it at Linux Foundation called Open Horizon at the LF Edge project. One last thing I'm going to mention. We did some work with Samsung. We have modified the Android kernel to now host a Docker runtime in Android, which means that all the things that we've been doing in terms of containerizing AI and machine learning algorithms, we can now also run on an Android mobile device as well. That's still experimental right now. We expect to have a formal release of that sometime next year, but this dramatically expands the utility of mobile devices in the world of edge computing and AI. So I'm going to end there. I want to thank you guys very much for your time. Sorry for going over a couple of minutes. or QR code to more information, lots of links to other data that you can provide, that you can look at to learn more about what we're doing. Thank you.